In 3,
Cool.
2. Oh, well, welcome everybody. Today we are very excited to have Massimo Caccia present their very recent paper, Task-Agnostic Continual Reinforcement Learning in Praise of a Simple Baseline. Massimo is a student at Mila and did this work while interning at Amazon Web Services. So Massimo, we are very excited to hear your talk today. I don't think we get enough continual reinforcement learning in these talks, and definitely not enough for my taste. So this change of pacing is going to be very exciting, I think, for everybody viewing today. So
Nice.
without further ado, go ahead and take it away. The floor is yours.
Okay. Thanks, James. Okay. So yes, I will talk a lot about continual reinforcement learning today. And yes, this is in the context of a Amazon internship. And it was done, this work was done with all these beautiful people. So today I'm not going to present a new fancy method. I'm just going to talk about baseline and how awesome it is. So I'm going to give a little TLDR so that people can better judge if they want to tune in or tune out of the presentation. So, okay, if you're like me, you've been working in continual learning, or more specifically in incremental image classification for a while, and you've been focused on maybe solving catastrophic forgetting or maybe developing some task inference tool. But your main motivation is not incremental image classification. It's more about developing these little agents that we could drop in the world, and they would be autonomous enough to learn about the world and accumulate knowledge and eventually reach general intelligence. Okay, so maybe it's far-fetched, but if you're like me, that's your main motivation, these little roaming robots that learn about the complex world. So basically the message of today is, if that's your motivation, then when we do deep learning in the context of in scenarios that look more about this main motivation, then the catastrophic forgetting problem and the task inference problem are not so important anymore, which begs the question, how important are the tools that we're currently building for this ultimate use case of continual learning? So hopefully you understood a bit what I'm going to chat about. I'm going to make things much clearer now. So here is an overview of the presentation. I'll try to keep the presentation self-contained. So I'll do a bit quick presentation of continual learning. Then we're going to dive into reinforcement learning. I'm not going to go too deep, but I need to explain like a bit of like MDPs and PalmDPs to set the stage for Task-Agnostic Continual RL, which I'll explain afterwards. And then what will be really important to understand is like these soft upper bounds that we usually use in continual learning or in continual reinforcement learning, which we'll call the TaskAwareness upper bound and the multitask learning upper bound. So I'll talk about these bounds a bit. And then I'll talk about some methods, the awesome baseline, and then we'll jump into the really surprising findings, which I think are great news for us. But I'll talk about that in the discussion. Okay, so continual learning. Everyone here is an expert probably, but I'll still give a slide presentation. My definition, at least, of continual learning is that we're trying to develop these learning agents that can accumulate knowledge on non-stationary data distribution. Okay, so the key word here is non-stationary data distribution. Why would this be important? Well, the world is non-stationary. So if we want to develop agents that can learn in the world, I think they need to be equipped with continual learning. There's other motivations for continual learning. You could develop an application that would need to handle non-stationary data. Maybe your application is impacted by the news, or maybe there's new users every day or new items every day. So your application needs to stay fresh. So that's another application of continual learning. And one last argument for continual learning is, for me, is the curriculum learning argument. Maybe you're trying to build this system or this robot that wants to achieve, wants to learn task X, but task X is too hard to learn from scratch. The randomly initialized neural net is not sample efficient nor compute efficient to learn that task from scratch. Needs to learn task A first and then become a bit more sample and compute efficient, then task B, and so on and so on. And when it reaches task X, it can learn it. So that's another argument for continual learning. So now that you're convinced that continual learning is important, right now, things sucks because deep learning cannot learn on these changing data distribution. When a neural net learns a task and then learns another task, its performance on the first task completely drops, and we call this the catastrophic forgetting problem. So even though I think we're really excited about this idea of like learning faster, learning better, because we're accumulating knowledge, right now the field is mostly focused on solving this catastrophic forgetting problem. So that's continual learning. Reinforcement learning. Okay, so reinforcement learning. There's an agent in an environment. This agent is in a state, and the agent will take a particular action in that state, and the environment will give that agent a reward for its action, and then will throw the agent in a new state. Okay, so that's reinforcement learning. And the goal of reinforcement learning is basically to find a policy that will accumulate as much reward as possible in this environment. And this objective is non-differentiable. So RL deals with all the fun that you get from maximizing non-differentiable objectives. Okay, so that's RL, little agent in the world, maximizing rewards. Reinforcement learning is most of the time framed in a Markov decision process. So Markov decision process, what you need to know is that in this world or in this environment, the states are fully observable. Okay, so you have this agent or this system, and basically its sensors are observing all of the variables that is important for that agent to take optimal actions all of the time. Okay, so this agent sees all of the world, and the states are Markovian. So in any state at any moment, everything that I'm currently observing gives me all of the information I need to take optimal action. I don't need to remember anything. Okay, so that is really constraining, but it's a good framework to develop algorithm in because it's more tractable than what we'll see later. So with MDPs, you can do some cute things like play certain video games or play some board games, but it's pretty constraining for real world applications, which brings us to the PalmDP. So PalmDP, really simple. You take the MDP and you remove the full observability assumption. So now your agent or your system doesn't get to observe all of the variables that are important to it all of the time. Okay, it only sees a subset of those variables. Okay, so now we can play more interesting games like poker, where you can think about the hidden variables as the strategies that your opponent is playing and like what hands that he have right now. And you can do even more interesting stuff, like maybe you can build robots. So why do I think a robot operates in a PalmDP and not an MDP? Well, think about a robot that is helping you build your house. Well, the robot is not gonna observe at all time the current state of the house, right? It needs to keep in memory where the house building is at, such that it can take its optimal action, which could be to take a walk to go get a brick and bring it back, you know? So it needs this kind of memory about the state of the house to perform optimal actions. So it's operating in a PalmDP. Okay, and I think that us humans, we definitely operate in a PalmDP. Like right now, my portfolio is changing because action prices are changing, but I'm not observing this, but it's relevant to me. And my paper is getting reviewed, but I'm not observing that, but it's going to be relevant to me. So I definitely think we're operating in a PalmDP. And I think that we are trying to accumulate as much information about the hidden state of the world. Yeah, I think that's what we humans do, because more information we have about the hidden state of the world, the better our actions will be. Okay, so now you know what a PalmDP is. Now I'm going to talk about what Task-Agnostic Continual RL is. Okay, and because I love getting massages, my running example will be a massaging robots. Okay, so we'll start with the PalmDP, which is overly general, and we're going to make some assumptions to get an object that is more aligned with what we want to study and more manageable. Okay, so we start with the PalmDP, and now we're going to assume non-stationary hidden states. Okay, so what do I mean by that is go back to the massaging robot. Let's say it has clients that likes it rough and clients that likes it soft. Okay, so by non-stationary hidden states, I'm saying we're going to assume some local stationarity. So we're going to assume that the robot is massaging someone that likes it rough for a while, and then maybe after 3 hours, it's going to switch to someone that likes it soft, and so on, so on, so on. It's not going to change at every second. Okay, the robot is going to get to take some time to infer what the human likes, and then do some of that, the massage that the human likes for a while. You know, it's not going to hop around between rough and soft at every second. Then we're going to assume passive non-stationarity. So this agent, it doesn't have a cause on the hidden state of the world. So in our case, it doesn't choose if the client likes it rough or soft. It is only responding to whatever the client wants. So that makes the PalmDP more manageable or more tractable. And then instead of assuming a humongous hidden state, we're just going to have one hidden state here. Okay, and it's actually just going to be a categorical variable that tells us which context we're in, and we're going to call this a task. Okay, because that's what we do in continual learning. Everything is a task. And now, so this is what Task-Agnostic Continual RL is. Okay, so PalmDP, local stationarity, just one hidden state, which is the task that I need to infer, and then I do not have a choice on what task it is. I'm just responding to that task. And then in Task-Agnostic Continual RL, just like in continual supervised learning, we're going to do task 1 for a while, then task 2 for a while, task 3 for a while, and then we're going to see, am I at the end of my life, am I good at all of those tasks? Okay. So yeah, it's the other way to think about Task-Agnostic Continual RL is it's like Task-Agnostic Continual supervised learning, but you're in reinforcement learning now. So, no task boundary, no task IDs, and so on and so on. You need to build these autonomous agents. So that's Task-Agnostic Continual RL. And now I need to talk about some really important bounds that we normally use in continual reinforcement learning, and we also use in continual supervised learning. So the first one is the TaskAwareness upper bound. In order to understand how much is lost from not observing all of the world, well, we're going to build baseline that observe all of the world. Okay, so we're going to give them the task ID, and now the PalmDP collapses to an MDP. So this should give us better results, better performance, and we should understand what is lost by not observing the full world. Okay, so continual supervised learning, this is like going from class incremental learning to task incremental learning. Okay, I'm sure you understand. The other bound and most important bound is the multitask soft upper bound. So now I'm just going to, instead of training on non-stationary data, I'm going to train on stationary data. This is what we call the joint upper bound or whatever. It's just like standard machine learning. Okay, there's no more catastrophic forgetting. And now we'll understand better what is lost by learning on a non-stationary data distribution. These two bounds are really important for the experiment section, which I will go in soon. But now I'll just take a slight detour towards the methods. And so I've said a lot of things right now. Probably not every component was understandable. But if you go in the paper, I wrote a little nice mathematical framework to think about the different objects I've mentioned, like Task-Agnostic Continual, RL, and HMM, PalmDPs, and so on and so on. So if this is interesting to you, section 2 of the paper with the nice table, in 2 minutes, you can understand the space better. Okay, methods, slight detour. So all the experiments that I will talk about are done with the soft actor critic reinforcement learning algorithm. I'm just going to give a really, really quick explanation of what I think it is, and then we'll go to the experiments. So SAC is really popular. It's a lot of papers built on it. So what is it? Starts from Q learning. Okay, so I'm not going to give you an RL class, but Q learning is super simple. You're learning this table of states and actions, and then you're trying to learn how valuable states and action pairs are, and then your policy is implicit. In a particular state, I'll just take the best action. Okay, so I'm just learning this state by action table, and this is my algorithm. That's Q learning. But if you have a humongous state space, this is not going to work, right? If I may think about it, if you're in pixel space, your state space is just humongous. You're not going to learn a table that has one dimension that is all the combination of all the pixels. You need to be smarter, and one thing you can do is deep Q learning. So my Q function, instead of instantiating it as a table, now is going to be a neural network that tries to predict the values of state and action pairs. And again, the policy is implicit. I'll choose the action that gives me the best value for that state. Okay, but that only works in discrete space. And in this work, we want to do some cool manipulation robotic task. So we need something that works in continuous space. And this is where SAC comes in. So in SAC, there's still this DQN thing, or a Q value that's parameterized by a neural network. We're going to call this a critic. And now, in order to have a policy that takes the best action, we're going to train a policy that maximizes the critic. Okay, so it's kind of like, if you squint your eyes a bit, it's kind of like a GAN, where there's like one model learning something and the other model learning some other thing by extracting information from the other guy. So here is the same. The policy is learning what to do in the world by maximizing the critic, which knows how valuable state and action pairs are. Okay, so that's all you need to know. That's soft actor critic. It's an awesome algorithm. Everyone uses it. It's hard to beat. It's awesome. Okay, now I'm going to talk about the baseline that is at the center of this work. Okay, so we have a partial observability problem, right? So this most standard way you can handle partial observability is to endow your model or your agent with a working memory, so that it can do some work and remember this work, or do some exploration in an environment, and then to understand what context it's in, or to understand what task it's in, and then remember that And then once the task is inferred, apply the policy that is good for that task. Okay, so we're giving our agent a memory to handle this PalmDP, and a good way to give an agent a memory is to give him an RNN, right? So we're just going to give whatever, we're just going to give our SAC backbone an RNN. Okay. Now we still have a forgetting problem. So we're just going to give our SAC backbone a humongous buffer to store all of the past so that it can retrain on the past. Okay. So we're combining an RL algorithm with an RNN and experience replay. We call this replay-based recurrent RL or 3RL, and that's our baseline. Okay. So we're going to talk a lot about this guy in the empirical findings. And then of course, we need baselines, more baselines for the paper. So the strategies will be either fine-tuning. So I'm just training a model that on the current task, and I don't care about the past. Then there's experience replay, where I store data on the buffer, and now I'm sacrificing some of my compute on the current task to put it on old tasks so I can remember them. So I'm sacrificing the current task for the old task. And then we're going to have this multitask strategy to give us the task out to the multitask upper bound. So that's like our 3 strategies. And then on top of those, if we're in the task aware setting and we're allowed a task ID, well, we're going to use it to give us some task aware upper bounds. Okay. So the simplest way to do it, or not the simplest way, but the most standard way to do it, is the multi-head. So super simple. Instead of having a single neural net or a single policy that does all of the tasks, now my policy enjoys one head or one output layer per task. And then I just use the task ID to retrieve the good head in training and in testing. Okay. So now, let's think of a stupid example. This robot has to do 2 things. I do 2 things. Maybe it opens the door, or maybe it closes the door. Well, as I reach the doorknob, both of my heads are going to tell me to continue reaching the doorknob. But when I get at the doorknob and I grasp it, now one head is going to tell me to push, and the other is going to tell me to pull. Okay, so that's multi-head. And then the other super simple thing you can do is just feed the task ID in the neural network, and let the neural net figure out what it wants to do with it. Okay, so that will be the baseline. So with this, you can construct some task aware upper bounds, some multitask upper bounds, and so on and so on. Okay, so now, super important, I need to talk about the benchmark we studied, and that's really important for the conclusion. So previous task agnostic or previous continual reinforcement learning work, I think on the task similarity spectrum, they are either too high or too low. So most of the time, continual reinforcement learning will be instantiated in these little toy Mujoko tasks, like an ant running around. Okay, and then one task could be to go in direction A, and then the other task would be to go in direction B. But between me and you, if you learn to go in a direction, you learn to go in all direction. So all of the tasks are just the same, but under slight variation. And I think this is really not representative of our use case of like deploying this agent in the world. And it's autonomous enough to learn about everything. I think we need to do something smarter. On the other end of the spectrum, we've been also doing continual RL in these Atari games, but now the tasks are just so different. There is not much reason to think that practicing Pong will make you better at doing a Mario game, So I think, again, that's not representative of the world. In the world, sometimes you learn something here that can be used there. So we need something more in the middle in terms of task similarity. We need a benchmark where the tasks are not the same, But in the task, we can learn something that can be reused for another task. And this is where robotic manipulation tasks come in. So in this work, we've played with Meta World, and which then some follow-up work made into a continual learning benchmark, which they call Continual World. So basically, we're going to be doing 10 or 20 tasks that are related to each other. And don't be confused by the rendering here. In the rendering here, this is just for human vision purposes. The algorithm doesn't see what you're seeing. It's not in pixel space, because in pixel space, it would be really trivial to understand what task you're doing. But the algorithm doesn't observe the same thing that we're seeing here. It's really a PalmDP in its mind. It really needs to do some exploration to understand that, oh, it's playing the basketball game. Okay, now you understand the benchmark. Now we're jumping into the findings. So first finding, somehow this TaCRL thing is always doing better than the task-aware method. Okay, so I done a gazillion experiments with the Amazon Compute, and I was always seeing this, and I just found it weird and interesting. And we're going to try to understand why that is. But yeah, we're like, it's like in continual supervised learning world, it's like your class incremental algorithm is always beating your task incremental algorithm. Like, you would be surprised, right? Then, which was even more surprising, was that this TaCRL, it was getting the same performance in continual learning than in multitask learning. So there was kind of no catastrophic forgetting problem. Or maybe there is catastrophic forgetting problem, but there is some advantages to learning on non-stationary data that overcompensate it. But when I saw that, I fell out of my chair like this guy, because that's kind of like the starting point of continual learning. Is like, oh, you cannot work on forward transfer yet. You need to work on solving catastrophic forgetting. So when I saw that, I wanted to investigate further. Why are these soft upper bounds not soft upper bounds anymore? What does it mean? So now what we're going to do is we're going to test some hypotheses as to why this could be happening. Okay. And we'll start with the ones that were falsified. Okay. So the simplest reason why the RNN would beat the task awareness upper bound would be that maybe the RNN is just better at learning MDPs. Like, maybe it's just better at learning each task individually. And this is why it is better than the other guys, okay? So what we did is we trained SAC, our backbone, on all of the tasks that we have studied, but now we're learning them in independent ways, so always from scratch. And we did the same with the SAC plus RNN. And what we saw is that SAC was better than SAC with the RNN on all those tasks. So it's not because the RNN is good at learning single tasks, which would be really weird, because each task are MDPs. So you should not need an RNN, because the world is already fully observable. Okay. Second hypothesis. If you're knowledgeable of continual learning, well, you know that successful methods, they mostly, what they have in common is that they will increase the parameter stability of the algorithm. So, you can do this in a soft way with regularization, like EWC, which restrains you from drifting too much in parameter space. Or you can do this in hard ways, like PACnet, that freezes the parameters, adds some new more, learn these new parameters on the new task, freezes those, and so on and so on. So now we're injecting hard parameter stability in your algorithm, and this can be good for catastrophic forgetting. So maybe an hypothesis is that this RNN somehow is stabilizing the parameters of the agent. So what we did is we've monitored how much the parameters are moving around during each epoch of training, as the agent was completely unexpected, which is that so in task 0, you're seeing that the parameters are stabilizing, and then once you start to learn new tasks, the parameters are like now moving more around. And as you learn more and more tasks, your parameters are moving more and more around. So it's like the algorithm is finally understanding what the parameters should be, and then a new task comes in, like, oh, okay, now I need to go back over and change everything, and everything is bad. So all of the weights are moving around a lot. So basically, this hypothesis is really wrong. The RNN is definitely not stabilizing the parameters. And so here you see like 3 methods and their parameters moving around. And yeah, all of the methods, their parameters are moving a lot around. Okay. Which brings us to the last hypothesis that we'll discuss today, which I think is the good one, and I think is the super exciting one. And this hypothesis is that the RNN, it correctly places the new task in the context of previous ones. Okay. So basically, it's recontextualizing the new task in the previous ones. So let's say, stupid example, task 1, robot needs to reach a doorknob. Okay. Task 2, the robot needs to open a door. Well, when the RNN or when the agent is learning task 2, maybe the RNN can correctly infer that the first part is just to repeat task 1. So it's just going to use task 1's policy when it reaches the doorknob. Okay. The model that don't have this RNN could not do this. They could reuse old skills, but they don't have a mechanism to infer that task 2 in this case, it can be decomposed in task 1 and some new subtask. Okay. So hypothesis is that the RNN correctly places the new task in the context of previous task. So now how the hell can we test for this? Okay. So it's hard to test for, but we can look for some effects that this would have on learning if it was true. Okay. So if it was true that the RNN recontextualizes correctly the new task, well, one thing we would see is that the RNN learns faster, right? It might even learn. So, okay, so now I need to give you a bit more context. In this benchmark, it's still always better normally to learn a new task from scratch, okay? Probably because you're not doing replay to remember the old task, so you're gonna learn this new task faster. But yeah, that's still the state of things. So now we're gonna look at the speed at which the RNN and the baseline are learning. So sorry, this is a really bad plot, but what I'm trying to focus on is the really, really top part of the graph where we see that TaCRL reaches in the 3 tasks. Okay, I need to give more context. In this continual world benchmark, not all tasks will be learned by the continual learning techniques. Okay, some are too hard to learn while trying to learn all of the tasks. So here you can see that task 0, 2, 5, and 8 can be learned by the continual learning methods. And then the independent method, the one learning from scratch in purple and yellow, maybe they can learn a bit the other task. Okay, but now we're going to focus on the task that the continual learner learned. And first, we're seeing that TaCRL is definitely the fastest of the continual learning method, but also more interestingly, it's even faster than the methods that are learning from scratch. Even though it's kind of spending most of its time replaying old tasks. So I think this puts some weight, or it supports the hypothesis that the RNN is able to recontextualize the new task and enable some forward transfer. Okay, so I think that's super exciting because I love forward transfer. This is why I'm into continual learning. One other observation, that's a trickier one. One other observation would be that if the RNN is able to recontextualize the task, it would suffer from less gradient conflict. So what do I mean by gradient conflict? Let's go back to the open the door and close the door example. If I don't have task IDs, or so if I'm not task aware and I train on this push and pull task simultaneously, well, I'm going to get conflicting gradients, right? Like in my buffer, there will be some examples that are telling me to pull the doorknob when I have my hand on it, and some other example that telling me to push it. I'm going to get conflicting gradients. These conflicting gradients, normally they can be alleviated with the task ID, or with the multi-head. But what I'm trying to get at is if the RNN is able to recontextualize the task and place them in the same set of contexts that are repeating in each task. Sorry, that's a bit confusing, but what I'm trying to say is if the RNN is able to give a representation to the agent that tells it, hey, when you reach the doorknob, in this context, you need to push, and in this context, you need to pull, then we should see less conflicting gradient, right? Which are going to be great for learning. So how can we test for this? Well, what we looked at is the variance of in the gradients at the mini batch level for each of the method. Okay. Previous work, they look at the angle between gradients. I think that's not good. We can discuss it further if someone wants to hear my argument. But for now, let's look at the variance in the mini batch, and then let's think about it as a proxy for gradient conflict. Okay. So now on the x-axis, you have the gradient variance, and the lower it is, the less conflict you have. And on the y-axis, you have the performance metric, basically, that's standardized. Okay. So first thing we see is that indeed the RNN enjoys more gradient agreement. So it goes in line with the hypothesis of recontextualization. And then here, the size of the bubble, okay, it represents how stable the learning is. Okay, so basically I'm monitoring the changes in the Q values of the algorithm. And I'm assuming that if they change a lot, it means that training is unstable. So, and this bubble size is in log space, just to make it fit here. And you can see that even in log space, the TaCRL has more stable training. So again, I think that this validates the hypothesis of recontextualization, and which I love because I think it's going to be good for the future of continual RL. And then one last thing, so some qualitative support for the hypothesis, and this is where I'm going to end the presentation. So here what you're seeing is the representation of episodes in different tasks as the RL algorithm learns in its life. Okay, so if we focus on the first one, before training, two things here. We see that, so here I assume that there's like 200 supposedly like 200 time steps. And now you see that the RNN is, the representation is quickly collapsing after a couple of time steps. So the latent space is not really rich. It's not really aligned with the tasks, you know. And the initialization, so the star, which is the representation of the first state, they're kind of like not at the same place. Okay, so the first state, its representation, is not invariant to the task, but it should be, because the first state, you cannot, it's impossible to infer the task from the first state, but there's some randomness in this first state. So the RNN needs to be invariant to this randomness, and we're not seeing this here. Okay, so the agent learns one task, the red one, and now we're seeing like longer trajectories, more rich trajectories, so we can hypothesize that now the RNN is kind of decomposing the episode into these smaller contexts that evolve. And then at the end, once all of the tasks are learned, well, the first states, they have correctly converged. And now all of the tasks have these like rich trajectories, which also overlap at certain stages, which tells us that maybe, like for example, they open the door and close the door. Well, at the beginning, right, they should touch each other. And so we're seeing this like interesting overlap between the tasks. So I think that this is at least some qualitative support for the hypothesis. And yes, that's it for the empirical findings. And then, okay, so I'll finish with some quick discussion. What does this mean for continual learning research? Well, if you're not like me, and this little agent dropped in the world was not your main motivation, and you're really interested in like these maybe more industry aligned problem of continual or incremental classification and so on and so on, well, you know, this work doesn't have any impact on you, I think. But if you're like me and you like this little agent roaming in the world, well, you know, maybe my findings are not generally applicable to all of task-agnostic continual RL, but I think we need to start thinking about how we need to start validating more if this task-agnostic continual RL use case is really a motivation for developing catastrophic forgetting and task inference tools. Okay, so yeah, and if we can replicate this finding, well, I think it's really great news because we can stop focusing on this boring catastrophic forgetting and now try to develop these maybe these methods where we focus on improving the sample efficiency and the compute efficiency of these learning agents so that they can eventually learn really, really complex tasks, which is the ultimate motivation for me in continual learning. And also, why is this happening in some continual reinforcement learning case and not in the continual supervised learning case? Well, I think that the two main things are, one, in most continual reinforcement learning case, your action space is fixed forever, okay? You're always, for example, in robotics, you're always moving the same, let's say, arms and legs. But in continual supervised learning, at least in the classification case, this action space or the space of your output classes keeps increasing and increasing. And then with the softmax, you're getting like the probability to predict the old classes is getting pushed down at every update. So because we're not suffering from this in continual RL, this maybe hints that most of the catastrophic forgetting problem is coming out of this badly calibrated softmax layer. Okay, I think a lot of work are pointing in that direction. And then the other difference between my setting and incremental image classification is that in the robotic manipulation task, there's really some things that you can reuse from task 0 on task 3 or on task 1 to reuse on task 4, right? There's some reaching and placing things, or you learn how to grasp an object and then this object comes back later. So it's definitely fertile ground for this forward transfer. But in image classification, it's unclear if that's the case. So yeah, I'm going to leave it like this, some food for thought. I hope that you've enjoyed the presentation, and I see that I didn't post any link for the paper on the slides, but you can just Google Task-Agnostic Continual RL, and it will come up. So yeah, thanks for listening. Thanks for letting me talk. That's it.
Awesome. There's been some wild chat discussion on YouTube happening that I'll try to fill you in on a little bit. But first, people want a clarification. My understanding is that there are hard task boundaries. It's just the agent is not aware of them. But are the task boundaries hard? Okay.
Yep.
So for those listening on YouTube, we have that clarified. We also had some.
It would be interesting to study like soft task boundaries for sure. But yeah.
We had some prophetic work from Blake Camp, who earlier made a comment saying that it's a great talk so far, but he made one small point. I think I would disagree that this stationary baseline should define an upper bound, and then a few minutes later you discussed that, oh look, maybe there is some nuances here, and it clarified soft upper bound, which is what we agreed with on the chat.
Yeah, so that's why I'm using the word soft, because they're not upper bound anymore. And they were really never like hard upper bounds, like in theory. So I think the word here is soft. Soft upper bounds.
I did want to make one comment at the very end of the discussion. You were talking about comparing this to class incremental learning.
Yeah.
I do think in general we're starting to converge in these past 6 to 12 months that that problem is very distinct from continual learning, in that it's this expanding classification task, and there's all of these like nuanced things happening with the expanding classifier and biases and stuff. So I think it's very refreshing to see that maybe catastrophic forgetting is different when we're actually looking at different tasks. I had a controversial tweet about a few weeks ago where I said something about, tasks versus tasks. It's an overloaded term in continual learning. And I think this is kind of discussing on how that may be true. Like we have, a task sometimes can mean different data coming in, but sometimes it means entirely different inputs and outputs like this, which I think is a different problem. Let's see what I can.
It's cleaner in continual RL. Well, at least for me, the second the MDP changes, then that's a new context, which sadly we call task.
I think we could do the same thing in Vision if we trained a classifier, but then trained a detector on top of using the same embeddings, and trained segmentation and overloading an encoder with different quote tasks. But let's see, Jonathan, and anyone who is on Teams right now, feel free to unmute, and I will hand the floor over to you to ask a question. In the meantime, I'm going to ask a couple of things from Sam Kessler. Go ahead.
Hey, can you hear me?
I can hear you perfect.
Awesome. So yeah, great talk, and really interesting, and great to have more talks on continual RL. So one question I had was, so I'm still a little bit confused about why 3RL does so much better than if you just gave a multi-head experience replay SAC agent the task ID. So I was just wondering, maybe you could just recap why you think it does better, and also how are you conditioning on the task ID? Are you just passing that in as an input, or in one of the like the final hidden to output layer of the queue function and the policy from SAC?
So I'll answer your second question first. the two task-aware baseline, they're either to have a multi-head. So now I learn my Q value and my policy, they learn like a shared representation of the task. And then I have a output head that will, in the policy case, choose the best action according to the task. And in the Q value case, choose the value of the state given the task, you know? So if you do continual supervised learning, it's really the same. It's one head per task. And then the other baseline is just, I'll feed that task ID to the model and let it figure out what it wants to do with it. Okay, so that's the two task-aware baselines we have in the paper.
Okay.
Did that help?
Yes, absolutely. And
okay. Yeah, so second part. Yeah, so why the hell would this RNN do better than this multi-head or this task ID baseline? Well, it's really what I'm trying to get at with this hypothesis 3, that the RNN is learning about the world, and it's basically what it's doing is it's converting trajectories of state actions and rewards into useful representations. Okay, that's its job. And normally we use this, and we're saying that we would hope that the representation that the RNN gives us is close to the task ID, so that we can reach the performance of those task-aware soft upper bounds. But what the RNN can do is also it can decompose a task into the different stages of the task, because it has a working memory. And when it's dropped in a new task, and it's given some rewards about it's doing some exploration on the new task, well, this RNN, it can maybe infer how this new task relates to the previous ones, right? Because the RNN job is to encode trajectories. So maybe if I go back to the task 1 is to reach a doorknob and task 2 is to open a door, when the algorithm is in task 2, well, if it's getting the same encodings in the first part of the task as in task 0, well, it can understand that it can reuse the skills of task 0 to learn faster this task of opening the door. So it's really about this recontextualization of new tasks in the past task that I think the RNN can learn faster. The task-aware method, they're not really equipped to recontextualize the new task in the past task. They're just, someone is just telling them, hey, this is a new task, figure it out, you know? I hope that was clear. It's the trickiness of the paper. It's really at the heart of the paper. But
yeah, I think there's definitely, I think you're absolutely right. So I guess because there's certain similarity between the tasks. So
yeah,
you know, one task could be, let's say, grasping a doorknob, or one picking up a ball. So all of them, you know, sort of require that sort of history. Okay, so let's say the current task is to pick up the ball, but obviously the agent doesn't know there's a ball, the ball is there. So it's going to first go take a look to see whether there's a door handle that's there, realize that there's nothing there, it's going to get a low reward, and then it needs to sort of re-explore and then sort of figure out, okay, no, there is a ball, so I'm going to, you know, I need to pick it up. So it's almost like it needs that history to be able to figure out, okay, I'm not in this task, I'm in a different task, and just sort of helps it become a little bit more robust. And I think this begs an interesting question, which is actually, if you had tasks that were very similar, if you put this RNN type algorithm, let's say with the Atari games, where there is very different state spaces, actually you might find that there's no benefit to the RNN in that particular case.
I think so. Exactly. I think that in an infinite compute world, I would definitely run that experiment.
Yeah.
And then in an even better world where we could really have a proxy of task similarity, it would be nice to see, like, have a nice curve of where the RNN is helping and where it's not. But you're right. The current hypothesis would be, if the tasks are really dissimilar, RNN will not help. If the tasks are really, really similar, then it's counterintuitive, because the RNN could help, but because all the tasks are the same, one agent can do all of them. So you don't really need the RNN. The task ID should be enough. But really, when you go to this interesting space in the middle, which I think is what most of the world is, then the RNN is useful.
Yeah. I guess you could also try it out on sort of like different mini grid or like mini hack type environments. There's kind of similar state spaces, but with different sort of end goals.
Yeah, 100%. I actually wanted to do that. Like, I wanted to try to find a simpler setting where I could launch a bunch of experiments and understand the behaviors better. But I left Amazon, and now I'm going to start some new things at another company, at DeepMind. So I have to kill the project, at least for now. But 100% some follow-up work on this would be, I think, amazing.
Yeah, cool. Thanks for answering, and great talk.
Thanks for the question.
I think we have another question on Teams. Let me quickly translate a couple of comments from online before you ask that question. I just wanted to translate. Blake Camp was pointing out that maybe was wondering if task labels could be causing some overfitting. Just kind of that's kind of a theory. And then another thing was Andre, I wanted to say that I really agreed about your perspective on the fixed action space. Could play like a big role on why that's explained.
So on Blake's point, I think that makes sense in a continual supervised learning world, but in continual reinforcement learning, I don't think overfitting can exist, because you cannot overfit the task, because you're tested on the same task that you're trained on. So not sure how you could overfit tasks, because the goal is to overfit the training task. So I don't know if Blake wants to review that. Could be fun, but yeah, that's my perspective.
Okay, and he may answer if he's still following along in YouTube, but I think we have one more question, and that may need to be it for time's sake.
Mm-hmm.
You want to go ahead and ask it? I can't see your full name on Teams. It just says Hemadi.
Yeah. Thanks, Massimo, for your interesting presentation. Actually, one of my questions was asked by Sam, so I'm going to go for the second one. Actually, in your hypothesis 3, I think it was that you said that variance of gradients can be kind of a metric for measuring interference in a batch. I'm not sure if I'm fully convinced that variance is a good measurement, because you could have like some samples in your batch where you have positive gradients, and you have some samples where you have negative gradients, but the variance can still be low. And you can have another batch where you have like this high variance, the same variance, but with lower interference. So you could have both cases. But to me, this more looks like low variance. It seems to be something like more positive forward transfer, because you have lower gradients variances. So yeah, this is the part that I was not.
Well, okay, so let me give you an argument for why I think gradient variance is a good proxy of gradient conflict. So you said something about having a negative. So let's say we're in one dimension, okay, and then I'm at 0, and then one gradient is telling me go a bit to the left, and then the other is telling me go a bit to the right. right? So if I was using, so normally what people do to monitor gradient conflict is they look at the angle between the gradients. So here the angle would be humongous, right? It's like the it's the opposite vectors, right? But essentially, both gradients are telling me the same thing. Hey, don't move around too much from where you are, okay? But if I have if I have another use case where one gradient tells me, hey, go a bit to the right, and the other one says, hey, go really far to the right. Well, now my angle is the same. So they're supposed to be really an agreement, but essentially they're definitely not telling me the same thing, right? So this is why I think variance gives you a good proxy of how gradients are aligned with each other. So hopefully that convinced you, but happy to discuss it more.
Yeah, so because I was not sure if you're measuring within batch gradient variance, or is it like you measure variance per sample in the batch, and then you, because this could be different if you would, I mean, you could have, like, for example, 10 samples in a batch. Some have gradients between 0 and 0.1, and some have 0 and negative 0.1 to 0. So you have like these two sets of samples in the batch. And
okay.
Yeah, so your range could still be fixed for two different types of batches, but the interference could be completely different because in one batch, all samples have this range of values from -1 to 1, but in the other one, a subset of them have only positive gradients and a subset have only negative gradients. So you would have basically the same variance for both. That's why I was a bit not.
Well, you would have the same variance for both, but the variance of the gradients would be high, right?
Yeah, I mean, you would have the same variance, yeah, but then the interference would be different because you have two different types of samples in the two batches. In one batch, you have two subsets where they completely disagree because of the only positive and only negative gradients, and in the other one, you have all samples which have the same variance, but all of them agree, which the values range from -1 to 1. So that's why I thought that this alone wouldn't probably say much about interference, but to me it more looks like if you have lower variance, it means you need less changes, so probably more positive forward transfer is happening in that model. Yeah, that's just something. Maybe if it's a long discussion.
I think but I think all of those things are related, and if your gradients of the past task are in the same, are not too well. I'm going to try to not use the word conflict because you seem to not agree on that part. So, but if their variants are not too big, then this should hint that learning this new task in the context of previous tasks should help. So I think we're thinking about the same conclusion, but we're just not exactly agreeing on the conflicting part. But the conclusion is the same. It should be good for forward transfer, this low variance thing. Well, I'll try to think about it more. Your argument.
I think Blake is online now if he wants to make a comment. I'm not sure if I well represented his comment earlier.
I do. Can you hear me?
Yes.
Great.
I'd like.
Hey, Massimo, how are you? Great talk. Thank you. I have two questions for you. One, to kind of build off what you were just talking about. One thing that I've been thinking about for a while is, given the success of some of the replay-free continual learners, I've been trying to think about whether or not the brain is simply robust to this representational drift, whether in the activations, the gradients, whatever you want to call it, or if it's the nature of the drift which is allowing very efficient learning in continual learning settings. So on the one hand, you can envision a model where it has some innate kind of parameters which are performing some regularization, and you kind of just assume that there's going to be some drift. And the distinction is, on the one hand, maybe the model is simply robust to that drift. And on the other hand, you can kind of think about a model that is explicitly pushing gradients in a particular direction. In other words, choosing where to push those gradients in order to kind of overcome forgetting and maybe learn faster. Just kind of curious if you were thinking about things in that way.
Yeah, well, I wouldn't know what horse to bet on, but the way I see things, if I were to put my neuroscientist hat on, which is really a bad hat for me, it would be that the human brain is probably much more modular than our neural networks, which are always updating all of their weights all of the time. So the way I think that the brain is able to not incur catastrophic forgetting without replay is that the brain is inferring context and then sparsely updating neurons to learn this new context or this new task. So when I'm learning how to ride a bike, I'm only going to update my motor skills neuron, and I'm going to keep my language neurons fixed. And I think this is why we're not seeing catastrophic forgetting so much. But yeah, that's just my 2 cents.
Great. And just one other quick question, which is, given the fact that, we're kind of seeing that you can approach that that stationary baseline, the multitask baseline, for performance, surely you must be thinking about ways to just start trying to exceed it, right? And so I'm curious if you've thought about just, pre-training your RNN in an effort to do that, and then letting the replay of your model handle the memory loss, because ultimately that's what we're trying to do, right? Is like, you can think of memory and generalization as two sides of kind of the same coin. Since old data may not always be available, it requires a type of generalization to still generate the right predictions for that. And so if you can do that in some sense, there should be a case to be made that you can start generalizing to true future data as well. And
I think so. There's this other interesting paper that basically says that so basically now they're studying PalmDP. So basically what they're saying is a lot of reinforcement learning spaces, they're just PalmDP special cases. Okay, like MetaRL is a PalmDP special case, robust RL is a PalmDP special case, and basically what they're saying is like, for all of these fields, if you are augmenting your standard RL algorithm with an RNN, we're doing on par with all of the methods that we have created for these spaces, including MetaRL. So essentially, this RNN, I think it can be good enough to infer new tasks correctly and perform them without further training. But of course, I think those tasks need to be really close to the training ones for you to be able to generalize to them. So it's a bit different than in our case, where the new task definitely needs more training, but the RNN can speed it up. But yeah, I'm not sure if I'm even answering your question. But
no, of course.
You said something at the beginning. You said, now the RNN can outperform the stationary soft upper bound, and that we should expect it. So I think that if you're serious about continual learning, it's because you think that one day will be better than multitask learning, right? You'll think that we'll get to a place where non-stationary, it's better to train on non-stationary data than on stationary data. maybe for the curriculum learning argument. Okay, so I think we're all hoping that this soft upper bound eventually evaporates for some settings, and then we can get better and better than it. So that's kind of why I'm super excited about this result. Is now we can reach this upper bound, and we can start thinking about how can we do better than stationary learning and start delivering on like some promises that we've made, like curriculum learning.
Yes,
which doesn't
exactly.
work.
And I was the advantage of pre-training is that you're not limited in your whatever that pre-training distribution is. So if you wanted to kind of encourage your RNN to generate super helpful feedback, well, one option is to just train on a huge number of tasks before you do your continual learning.
Yeah, no, that makes sense. And I think we're seeing this a lot in at least in the continual supervised learning case, where people are trying to start from pre-trained models, and I think that makes a lot of sense. And then it would be fun to see it in RL, like maybe start like DeepMind as a new foundation for RL, like a Gato. I think it would be amazing to see like I guess there's no RNN in Gato, but if there was one, see if it can continually learn faster than other methods. That would be cool. But yeah, thanks for your questions.
Thank you.
Awesome. I think this would be a good time to wrap up, but feel free to stay on MS Teams, anybody, if you want to discuss after we stop the stream. Thank you everybody for joining, and thank you for this wonderful presentation, Massimo. You can catch us again next week, same time, same place as our last seminar before the summer pause. We will hear from Samuel Kessler, who had just asked a question a few minutes ago. He's from the University of Oxford, presenting same state, different task, continual reinforcement learning without interference. So after a wonderful RL paper today, we'll have another one next week to close off this spring. So see you next week, everybody, and thank you again, Massimo, for the presentation today.